नमस्कार दोस्तों, मेरा नाम है शौविक and you are watching mathematics from basic YouTube channel. Thanks for watching. In this video, I am going to show a proof of the fact that rational number is dense over real numbers. Okay, so let's discuss. So as you can see in the screen, we need to show Q is dense in R. But before going to the proof, I will define uh, what do we mean by density. Okay, so let's start once again. What is, yeah, okay, so first comes definition. Let S be non-empty, A subset of R, then S said to be dense in R if for any real number R and for any epsilon greater than 0, there exists an element S in S such that S belongs to open minus R minus epsilon to open R plus epsilon. Okay, that is, if we take any real number R, if we choose very small enough open intervals R minus epsilon to R plus epsilon, then we can find S belonging to these intervals. Okay, so that's what we mean by density. So this is the definition. Now we are going to prove that Q is dense in R. So now coming to the proof. Sorry, somehow the pen is not working actually. Coming to proof. So according to the definition, what we need to do, we need to choose a real number R and need to choose a epsilon greater than 0. Then we need to consider the intervals R minus epsilon, R plus epsilon. Okay, now look that if if to call this interval R minus epsilon, R plus epsilon is equal to I. Okay, if 0 belongs to I, then of course done. Hmm. Now next there is two possible cases. Next is two possible cases. One is R minus epsilon greater than 0, and that is, in this case it will look like this. Here is 0, here R minus epsilon, here R plus epsilon, and in second class R plus epsilon will be less than 0. In this situation, the situation will be like this. Here we have 0, and here basically R plus epsilon. So somewhere here R minus epsilon is there. Okay, so first, so now we are going to consider this case A. Okay, so this is, now we are going to consider After doing this, we will come for B. Okay. So in that case, r minus epsilon greater than 0, without just um, for sake of writing, we will take r minus epsilon is equal to A and r plus epsilon is equal to B with A B greater than 0. Okay. Now, by Archimedean property, this is by Archimedean property, there exists n naught belongs to natural number such that 1 by n naught is less than b minus a. Okay. So then one second. So then consider this set S consisting of those natural number m such that m by n naught will is greater than a. Okay. Now so now the thing is that um, our claim is S non-empty. Okay. So what is the proof of this claim? Proof is that look, by Archimedean property, there exists an m naught such that m naught is greater than a n naught. Okay. So this implies m naught is in S. Okay. So as you can see here also the Archimedean property plays a role. So now coming back to the main proof, that is, so finally we get S is non-empty and S is a subset of natural numbers. So by this is by the well ordering principle, this is known as the well ordering principle. This principle says that every non-empty subset of natural number has a least element. So by this principle, there exists m naught least element, which is least element of S. Okay. So this means what? This means m naught by m naught by n naught, it is greater than a, and m0 is the least element, means m0 minus 1 by n naught does not belongs to S if and all this if and only if m naught minus 1 by n naught it is less than equal to a. Okay. Now okay, So now our claim is that m naught by n naught is, sorry, this thing is less than b. This m naught is basically this in m naught. Okay, so this is what we want to show. So what is the proof? Proof is basically the contradiction method. So if possible, if possible, let m naught by n naught is greater than equal to b. Then observe this equation and this equation together implies 1 by n naught is greater than equal to b minus a. Okay, so finally we get 1 by n naught greater than equal to b minus a. But observe that our 1 by n naught was less than b minus a. So it is a, of course, contradiction. So m naught by n naught is less than b and it is greater than a. Okay, so this is what we want to prove, where a is equal to r minus epsilon and b is equal to r plus epsilon. Okay. So we are done with this case 1. Now we will go for this case b. Okay, so the proof of case b will be done as follows. Proof of case b. One second, I'll be back within some minute. So for the proof of case b as follows. In this case b situation, we have what? We have r minus epsilon less than r plus epsilon. This is less than 0. This implies minus r minus epsilon less than minus r plus epsilon. Okay, with minus r greater than 0. No, observe that my r is less than 0 because r plus epsilon is less than 0. Okay, so now due to case a, we will get some m prime by n prime belongs to q, such that this will lie between these intervals minus r minus epsilon and minus r plus epsilon. Sorry. So again multiplying by minus sign, we will get what? We will get r minus epsilon less than minus m naught by m, m prime by n prime, which is less than r plus epsilon. Okay, so this is, sorry, this is what we want to show, that is between r minus epsilon and r plus epsilon we get a rational number. Okay, so we are done with the two cases, case a and case b. These two cases, case b is done and case a was already done, and we have already simply told that case, that this case one, if 0 is in I, and then of course we are done. Hence we are done all possible cases. So q dense in R. Okay. So as a remark, one can show exactly in similar way one can show this set M by p to the power n, where M and n are integers, n greater than or equal to 0. This is dense in R, where p any prime. Okay, so this can be shown in exactly the same way, and this is another dense subset of R. So these are the things which I want to discuss in this video. So this is the end of my discussion here. Once again, thank you for watching this video, and if you find this content somehow helpful, then please do like, share and subscribe and comment. Okay, once again, thank you. Bye.